Today, I'd like to be a little self-indulgent. It's not entirely self-indulgent because I have received several perfectly real and valid questions regarding today's topic. But it's mostly self-indulgent because that topic is indeed a subject near and dear to my heart. The vast emptiness that dominates our universe. You know it, everybody's favorite, the cosmic voids. I like to joke that I'm one of the world's top 5 experts on cosmic voids because there are 5 people in the world working on cosmic voids. Neither of those statements are entirely true, but I have been working on and off with voids for most of my professional career. And the truth is, I think they're pretty neat. So the question for today is, what's inside the voids? Like, really inside? Are they actually empty? What would it be like to live inside of one? I figure there's nobody better in the world to answer those questions, at least not anybody with a YouTube channel, so let's get to it. I'm Paul Sutter and I'm a cosmologist. Let's talk about the universe. To answer the question of what's inside a void, we first have to decide what a void is. I know it's easy enough to describe in big, broad, vague terms. Voids are the empty places. Voids are the things that aren't. If you zoom out to truly enormous scales, well beyond the sizes of mere galaxies, where you take such a huge portrait of the universe that individual galaxies appear as nothing more than tiny points of light, then A, welcome to cosmology, and B, holy crap, the voids really stand out. In fact, we got our first taste of the voids all the way back in the late 1970s, right when we started to build our first deep surveys of the universe. Once we started making maps, we noticed places where the maps were empty. And 2 different groups found the voids at around the same time, although only one group called them voids. The other group called them big holes, and for one, I'm glad they didn't win that particular jargon war. It took a few years for the rest of the cosmological community to accept that voids were real. Because if you see a gap in your data, it's easy enough to argue that, hey, maybe you didn't do all that great of a job when you were collecting your data. Or maybe it was just a trick of the eye, like we're seeing a pattern that isn't really there. But survey after survey kept having these big holes, and voids were here to stay. Before we keep going though, please consider subscribing to this channel to get more cosmology goodness, because I think you like this kind of stuff too. So voids are the places where there ain't a lot of galaxies, and they're easy enough to pick out by eye. You make a map of the universe and you find the big holes, and you can point to them and say, hey, there's a void right there. And we have a very solid idea of where they come from. When you zoom out to those same ultra gigantic scales, you see lots of cool stuff. Galaxies, filaments, walls, and clusters. We call this the cosmic web. And it's like a glittering city that stands out from the darkness. But just like any city, it had to be built, brick by brick. The matter to build the cosmic web had to come from somewhere, and it came from the voids. My favorite analogy is Paris, the city of light. Its unique white limestone is dug out from underneath it. If you've ever visited the catacombs, you're walking through the underground quarry that made Paris. The city of light is sitting on top of a void of darkness. But if we're going to be specific, and this is science, so being specific is a big plus, how do we define the edge of a void? Its boundary? What about its center? How can we categorically point to any one place in the universe and say, that point belongs to a void, and point to another place and say, nope, that's not in a void? Well, do we have an answer for you? It's called vide, which comes from the French word for empty, and our team developed this in Paris, which is how I thought of the name. Of course, it's a lame acronym for Void Identification and Examination Toolkit, and it's just the sort of nerdy thing that us scientists get excited about. It's also free and available to use if you ever want to go void hunting yourself, but sadly, no, I will not be devoting any portion of this episode to the technical details of how to use it. You're just going to have to read the manual like everybody else. There are a lot of ways you could potentially define a void. We chose one particular method because it seemed like a good idea at the time, and as the years have gone on, it has proven to be a rather good idea, which is part dedicated effort and part just luck. And in fact, today it is the #1 void finder in the world. Chances are that if you catch a new research paper about voids, and I know you subscribe to all the hot cosmology gossip, the research used VEED, our methods and tools, as its backbone, which is pretty cool. So here's how we decided to define a void. You start with a collection of galaxies or a map of the dark matter. It doesn't matter, as long as you're tracing where the stuff in the universe is. Then you imagine that this map is a topographic landscape, like mountains and valleys, where the mountains are the high density clusters in the filaments and walls. And then you imagine dropping rain onto the map and you follow where the rain collects. The basins where rain collects are the voids. These are the low density valleys in that topographic map. And the places that split the direction of raindrops are the ridge lines that separate one void from another. Yes, this is the exact same method used to find watersheds in actual topographic maps to find where water flows and any landmass. It's the exact same mathematics, just applied in a different context. This method is nice because it just automatically works for any kind of input. It doesn't have any tunable parameters, and it easily picks up voids within voids within voids. This is what VEED does. It takes in a collection of matter and spits out where all the voids are, how deep they are, how far they extend, and so on. With this tool, we've found thousands of voids in our largest galaxy surveys. So now that we have a collection of voids, we can finally ask, well, if we crack them open, what do we find inside? And yes, my friends, what we find inside, like a giant cosmic Kinder egg, is a Patreon ad. That's patreon.com/PMSutter, where you can keep this show going. I truly appreciate all of your contributions. There is a link down below. No, the real answer is a whole bunch of nothing. You probably could have guessed that on your own. But here's the thing. For a good chunk of their volumes, they're not completely, totally 100% dead and lifeless and empty. The analogy I like to use here are deserts. Sure, if you go out in a random desert, you may not find a lot of rain or activity, but it's not totally devoid of life. There are still, succulents and small mammals and reptiles. Listen, I'm not a biologist or expert on biomes, so I'm just winging it here. My point is that in a desert, there's still stuff, just not a lot of it. And if you take a picture of a void, or more accurately perform a deep galaxy survey within a void, we find that there's still stuff, just not a lot of it. We can see dim dwarf galaxies with thin threads of gas connecting them. We can't directly see the dark matter in our observations, but when we build computer simulations of the universe, we find voids there, and we see entire mini cosmic webs with voids divided into subvoids, divided into sub-subvoids. Yes, that means that there's a slight fractal character to the cosmic web, which is really cool, but not the point of today's episode. But still, even though the voids aren't totally empty, they're still pretty dang empty. A typical void will have somewhere around 1/5 the average density of the universe, which doesn't sound all that empty. But check this out. If you took all the stuff in the universe, every planet, every star, galaxy, wedge of cheese, gas cloud, and even all the dark matter, and smeared it out into a uniform ooey gooey mess across its total observable volume, the entire 90 billion plus light years extent of it, you would end up with an average density of roughly only one single hydrogen atom per cubic meter. A cubic meter it's big. It's about yay across. Imagine placing just one hydrogen atom in that entire volume. That's what the universe is like on average. But the vast majority of that stuff is crammed into very small volumes. I can assure you that the air you're breathing now is slightly denser than one hydrogen atom per cubic meter. Now, a typical void is only 1/5 of that. So a volume 5 times bigger containing only one lonely hydrogen atom. I don't know about you, but to me, I consider that kind of empty. And this includes the borders and boundaries of the voids that butt up against the walls and clusters and filaments. The boundaries of the voids are decidedly less voidy out of necessity, just like the edges of a desert that transition to, again, not too familiar with biomes here, like jungle seems wrong, as does ocean. Let's just call it not desert. There's just transition where it's slightly less desert. But it is possible to reach deep into the void, just like it's possible to reach deep into the deserts and find truly lifeless portions, like the Qattara Depression in the Deep Sahara, or the empty corner of the Arabian Desert, or Badwater Basin in Death Valley. There are deep regions within the void, far from the walls and boundaries, far from any dwarf galaxies, far from any loose threads of gas, where there's essentially nothing for up to millions of light years. Even this shows up in our dark matter simulations too. I mean, yeah, sure, if you wait long enough, you might see a random hydrogen atom wandering by, or a particle of dark matter zip on through. But you'd have to wait a really, really long time before the next one. And I can't help but wonder what it might be like to live inside a void. Imagine if we transported the solar system into one of those deep regions. Of course, there would be no stars on the sky, but it would be even worse than that. There would be nothing on the sky, just the sun, the moon, and the planets sitting against a completely blank canvas. It would take advanced telescopes to see even the nearest galaxy, and it would still only appear as a faint, dim smudge in the extreme distance, which leads to a really intriguing thought. If somehow we arose to intelligence and civilization on a planet in the void, would we even develop astronomy? Yeah, we would invent telescopes and get close-up views of the planets, but with millions of light years to our next nearest neighbor, would we ever bother refining our technology? Would we ever discover cosmology, the expanding universe, the Big Bang? Would we even know that the rest of the universe is out there? When I stay up way too late at night, I sometimes wonder if we're missing something ourselves. But I don't like that thought all that much, so when that happens, I just switch to playing Minecraft or something. But that's just matter. And we all know there's more to the universe than just matter. Nothing in this universe is completely empty, and that's because there's always your constant companion. Me? No, not me. I only visit once a month. For one, there are the neutrinos and the cosmic rays. These high-energy particles zip around the cosmos. They're blasted out by all sorts of fun and energetic processes like stars blowing up, stars getting torn to shreds, stars smashing into each other, stars getting eaten by black holes, and various and sundry star-destroying processes. Oh, and the giant black holes, the neutron stars, the white dwarfs, the giant molecular clouds, the fast radio bursts, the accretionists. I mean, there's a lot of astrophysics out there, isn't there? Anyway, all these processes tend to produce showers of particles that go flying out at nearly the speed of light. These include protons and other miscellaneous atomic nuclei, which we call the cosmic rays, even though they're not rays at all. But by the time we figured that out, the name had stuck. Anyway, different episode. And there are the neutrinos, which are the super light, ghostly particles that hardly ever interact with matter. On a typical day, if you're standing outside, about one cosmic ray strikes you every single second, and that's after many more have been blocked or absorbed by the Earth's magnetic field and atmosphere. As for neutrinos, on that same typical day, about 100 trillion neutrinos pass through you every single second, but they're so slippery that you should expect only one of those to ever actually hit you in your entire life. And if cosmic rays and neutrinos can do that here, they can do it anywhere. We know for a fact that cosmic rays and neutrinos can cross intergalactic distances because we've traced back their origination points, and lo and behold, they often come from other galaxies. This means that neutrinos and cosmic rays are constantly crisscrossing the voids, spending tens of millions of years in their traversals of the great cosmic deserts before reaching another galaxy. They don't exactly add up to much, however. Yeah, if you were sitting inside a void and had a sensitive enough detector, you would get ping, ping, pings as these particles zip through. And that's about it. In the deepest centers of the voids, besides the cosmic rays and the neutrinos and the dark matter that occasionally pay you a visit, there's still the ever-present bath of radiation. Some of this radiation is from starlight, although as you can imagine, it's not exactly going to add up to a lot in the deepest corners of the void. The nearest galaxies are so far away that they're only visible with the most powerful telescopes. So yeah, while they are technically sending you photons in your direction, it's not exactly a significant number. But there's more to the light in the universe than just stars and galaxies. In fact, even in our corner of the universe, which is a relatively dense neighborhood, starlight accounts for only an insignificant fraction of all the radiation in the cosmos. By far, the vast majority of light in the universe is due to the cosmic microwave background. The cosmic microwave background was created in an event that occurred when the universe was only 380,000 years old. At that time, the universe had expanded and cooled to the point that it turned from a hot, dense plasma into a slightly less hot, slightly less dense neutral gas. This freed the radiation. In physics, we like to call this kind of situation free streaming. The light was finally able to just traverse the universe without really encountering any significant collisions or resistance or absorption. The whole universe participated in the generation of the cosmic microwave background. Every part of the universe released that light, and that light has been traveling through the universe ever since. So no matter where you go, you're always surrounded by that radiation. When it was released, that radiation had a temperature of around 10,000 Kelvin, the same as the surface of a typical star. It was literally white hot. But it's been a while, and the universe is a lot colder and a lot older and a lot more stretched out nowadays. And so that intensity of radiation has really fallen off. And now it is firmly in the microwave band, hence the name cosmic microwave background. But still, even in that fossil state that has been preserved for over 13 billion years, the cosmic microwave background is responsible for something like 99.999%, and you could probably add a few more nines just to get the point across, of all the radiation in the universe. So even if you're in a deep void, you're still surrounded by the cosmic microwave background because the cosmic microwave background literally fills up the universe. However, even though it's present, it's not going to do a lot for you. Yes, if you have a sensitive microwave detector, you're going to pick it up. You're going to see that those photons are washing over you, even in the deepest corners of the voids. But the energy carried by the CMB is not a lot. Even though the CMB is by far the brightest thing in the universe, with by far the most amount of photons, there's a whole lot of universe out there for the CMB to be spread through. The temperature of the cosmic microwave background is a little less than 3 Kelvin. That's just 3 degrees above pure absolute zero. So if you were stuck in a void and had no other source of warmth, no other source of light, no other source of heat, you could at least rest assured that your frozen corpse would be prevented from reaching a temperature of absolute zero because of the presence of the cosmic microwave background. So you have that going for you, which is nice, I suppose, but also you're not going to really notice it on a day-to-day basis in the deep corners of the voids. But it's technically there, and like I said, this is science, and in science, precision matters, so we have to add it to the list. So if we take out all the matter, the neutrinos, the dark matter, the cosmic rays, and the radiation from the deepest parts of the voids, the only thing left is empty space. I know it sounds like a paradox, but the voids are full of the vacuum of space-time. And crucially, that's not nothing. That's because the vacuum of space-time has something inside of it, or on top of it, or within it, or kind of existing within its fundamental fabric. Look, it's kind of hard to precisely describe with words what's going on, but I'm going to talk about quantum field. In quantum field theory, the particles that make up our existence, like electrons and top quarks and neutrinos, and even the dark matter, aren't really particles. What we think of as a particle is really just a manifestation of a deeper, more fundamental object. These objects are the fields. There's a field associated with every kind of particle, and these fields completely soak every cubic centimeter of space and time. They have existed since the Big Bang, and they completely fill up every corner of the universe. When we point to something and say, oh, look, there's an electron zooming by, what we're really seeing is an excitation or a vibration or a wave of the fundamental field that is cohered and is traveling. But even if you take out all the particles, even if you take out all the stuff, the field itself remains. And that field has energy. It has energy through the Heisenberg uncertainty principle, which is a whole other episode. And when we go to calculate how much energy is in the vacuum, we get answers anywhere from an extreme amount of energy to literally an infinite amount of energy, which is also its own episode. But this energy has an effect. We call the effect of this energy dark energy, which is the cool name we give to the accelerated expansion of the universe. Now we know from dark energy and the rate of acceleration that we can measure in the universe that the actual amount of energy in the vacuum is not very large, but it's not zero. And the thing about dark energy or vacuum energy or whatever you want to call it is that in dense places in the universe, it doesn't matter. It has no effect. Here on the Earth, there's a lot of density of matter, and that presence of matter overwhelms any effect that dark energy might have. You could erase dark energy from existence totally altogether, and we here on the Earth would hardly ever notice. Trajectories of thrown baseballs would be exactly the same. Your burrito would still take the same amount of time to cook in the microwave. Nothing changes. The same is true for galaxies. The same is true for clusters. The same is true for filaments. The same is true for walls. The same is true for every part of the cosmic web, except for the voids. The voids are the places where matter isn't. The voids are places where the vacuum of space-time itself dominates. If you put yourself in the middle of a cosmic void, you are surrounded by dark energy. In fact, voids are the places where dark energy is doing its job of accelerating the expansion of the universe. It's not happening in any dense place like galaxies or clusters. It's only happening in the voids. The voids don't just empty out to build the cosmic web. The voids themselves are expanding. They are literally tearing apart the cosmic web. What we see as these very large and beautiful and intricate structures in the universe are temporary. Over the course of the next 5, 10, 20 billion years, the exact number doesn't matter, the cosmic web is going to evaporate. And it will do that through the action of the voids pressing against everything else. So the voids are full. They are vibrating with fundamental quantum energy. They are doing work on the rest of the universe to accelerate its expansion. And they are the only places in the universe that can do this. And the only reason they can do this is because they are devoid of everything else. So yes, voids are empty of matter. This is how we discover them. This is how we measure them. This is how we define them. But the emptiness of matter means that they are full of dark energy. And so no matter where you go in the universe, whether it's to a nearby galaxy or the deepest interior of the emptiest voids, you will never ever quite be alone. So what do you think? Are voids an interesting object in the universe or the most interesting object in the universe? Should we abandon all other research projects in the world solely to focus on cosmic voids? Am I personally biased in support of voids, or is it just a natural conclusion of the fact that they are amazing and fascinating? Let me know what you think in the comments. It's a big universe out there, but we'll take it one step at a time. Thank you for watching.